By now, you have likely been inundated with headlines about EV batteries, fast charging, long-range capabilities, and the technology of the future. But before we start, don't forget to subscribe to our channel. However, a development has just surfaced that is sending shockwaves through the entire global automotive industry. China's preeminent battery titan, CATL, is currently perfecting a new solid-state battery, a power cell capable of propelling a vehicle between 800 to 1,000 miles on a single charge while achieving a near-full recharge in a staggering 10 minutes. This is far more than a simple incremental upgrade. It is a fundamental shift that could rewrite the rules of the electric vehicle world permanently. Now, the critical question arises: is this a tangible reality, or is it merely corporate hype? If this technology truly arrives, what becomes of the internal combustion engine? Where will industry leaders like Tesla and BYD stand? And perhaps most importantly, is this future unfolding right before our eyes? Or is there a hidden truth that might shock the market? To understand how the future of transportation is being reshaped, we must first look at the architect of this change. Who exactly is CATL? In the volatile world of EV development, not every company's claims carry the same weight. But the moment the name CATL is mentioned, the entire industry pauses to listen. Standing for Contemporary Amperex Technology Limited, this Chinese powerhouse is currently the largest EV battery manufacturer on the planet. Their ascent was not accidental. Founded in 2011 by entrepreneur Robin Zhang, the company's DNA was rooted in high-stakes energy storage. Before CATL, Zhang was a key figure at ATL, which manufactured mobile phone batteries for global giants like Apple. He understood early on that the true currency of the future was energy density. As electric vehicles began their slow migration into the mainstream, CATL pivoted with surgical precision, pouring every resource into research, development, and aggressive scaling. Initially, they partnered with local Chinese innovators such as NIO and XPeng, but their reputation for reliability and technological superiority soon caught the eye of the global elite. Today, the world's most prestigious automakers, Tesla, BMW, Mercedes-Benz, Hyundai, and Volkswagen, all rely on CATL to power their fleets. Consider the weight of that fact. Even Tesla, a company that prides itself on being the vanguard of battery innovation, turns to CATL as a primary partner. This collaboration is a testament to CATL's unparalleled engineering capabilities. Currently, the company commands a staggering 35% share of the global EV battery market. Statistically, this means that 1 out of every 3 electric vehicles driving on the road today is powered by a CATL battery. This is not just market participation. It is absolute leadership in a sector worth hundreds of billions of dollars. Yet, their true strength lies not just in their massive valuation or production volume, but in their relentless pursuit of the next big thing. Whether it is lithium iron phosphate, LFP cells, sodium-ion alternatives, or ultra-fast charging solutions, CATL is consistently first to the finish line. Furthermore, they have mastered the art of vertical integration, controlling the entire supply chain from raw mineral extraction to the final assembly line. This control allows them to maintain lower costs and faster production cycles than almost any competitor. When other companies are still trapped in the experimental testing phase, CATL is already calculating the logistics of mass production. Therefore, when CATL's leadership speaks of a solid-state breakthrough offering 1,000 miles of range, the world does not dismiss it as a mere marketing claim. They recognize it as a roadmap. However, as CATL themselves admit, transitioning a laboratory miracle into a mass-market reality is a journey fraught with technical hurdles. To understand why this specific battery is causing such a stir, we must look deeper into the chemistry that defines the modern EV. Today's cars run on lithium-ion batteries which utilize a liquid electrolyte, a fluid medium that allows ions to flow and generate power. While effective, this liquid comes with inherent risks. It is flammable, sensitive to extreme temperatures, and limited in how much energy it can store. The solid-state battery eliminates this fluid entirely, replacing it with a solid ceramic or polymer interface. Imagine moving from a turbulent water path to a paved high-speed highway. That is the leap in efficiency and safety we are discussing. This shift promises to end the era of range anxiety and safety concerns forever. To truly appreciate why the entire automotive world is fixated on CATL's latest announcement, one must look beneath the surface of the vehicles we drive today. For over a decade, the electric vehicle revolution has been powered by lithium-ion battery technology. At the heart of these batteries lies a critical component known as the electrolyte. This substance acts as the medium, the internal highway that allows ions to travel between the anode and the cathode to create an electrical current. In almost every EV currently on the road, from the most affordable commuter car to the high-end luxury sedan, this electrolyte exists in a liquid state. Imagine a fluid pathway, much like a river, where energy must flow back and forth. While this has served us well, liquid electrolytes bring inherent physical limitations. The most pressing issue is safety. These liquids are often volatile and highly flammable. If a battery pack is punctured in an accident or undergoes a phenomenon known as thermal runaway due to overheating, the liquid electrolyte can ignite, leading to the intense fires that have occasionally made headlines. Furthermore, liquid electrolytes are sensitive to extreme temperatures and can degrade over time, limiting the overall lifespan of the vehicle's power source. This is precisely where the solid-state revolution enters the frame. As the name implies, this technology replaces the liquid medium with a solid material, typically a ceramic, glass, or specialized polymer. The fundamental difference is akin to moving from a muddy, unpredictable water path to a reinforced, high-speed concrete expressway. In a solid-state battery, the ions move across a stable, solid surface. This structural shift offers three transformative advantages that could render current EVs obsolete. First and foremost is safety. Because there is no flammable liquid, the risk of a catastrophic fire is virtually eliminated. Even if the battery is damaged or subjected to extreme heat, the solid electrolyte remains chemically stable, providing peace of mind for drivers and manufacturers alike. The second major advantage is energy density. In the world of battery engineering, space is the ultimate currency. Because solid electrolytes are much thinner and more stable than their liquid counterparts, engineers can pack significantly more energy-storing material into the exact same physical footprint. This is the magic bullet for range. It is the reason why a car that currently travels 300 miles could suddenly be capable of 800 or even 1,000 miles without increasing the weight or size of the battery pack. The third pillar of this technology is the potential for ultra-fast charging. Because the solid structure can handle higher temperatures and more intense electrical stress without breaking down, it theoretically allows for massive amounts of power to be pumped into the battery in a fraction of the time. We are talking about a full refuel in 10 minutes, matching the convenience of a traditional petrol station visit. However, a significant distinction must be made between theoretical brilliance and real-world application. While these benefits are clearly visible in a laboratory setting, scaling them for the global market is one of the greatest engineering challenges of the 21st century. Creating a solid material that is conductive enough to allow ions to flow freely, yet durable enough to last for 15 years of daily driving, is an immense hurdle. Many solid electrolytes are inherently brittle. They can develop microscopic cracks over hundreds of charging cycles, which leads to a rapid loss of performance. There is also the interface problem. Ensuring that the solid electrolyte stays in perfect, continuous contact with the electrodes is far more difficult than simply pouring in a liquid that fills every gap. These are the technical walls that have kept solid-state technology out of our garages for so long. But CATL is not a typical research firm. They are a manufacturing giant. Their approach involves solving these microscopic chemical problems at a macroscopic scale. By developing new hybrid materials and advanced coating processes, they are attempting to bridge the gap between experimental and executable. When CATL discusses 1,000 miles of range, they are not just talking about the chemistry, they are talking about the industrial machinery required to build it. This transition represents a shift from the lithium age to the solid age, a move that promises to solve the three biggest barriers to EV adoption: safety, range anxiety, and charging time. As we look at the specifications being teased, it becomes clear that we are witnessing the birth of a new era in mobility. While the promise of a 1,000-mile range and 10-minute charging sounds like a miracle, it is crucial to examine these claims through the lens of ground reality. Currently, The average electric vehicle in the United States offers between 250 and 350 miles of range. Doubling or tripling that capacity to reach 1,600 kilometers is a monumental leap. However, range is a complex metric. Most manufacturers calculate these figures under ideal conditions: constant speeds, perfect ambient temperatures, and flat terrain. In the real world, factors like heavy traffic, air conditioning usage, and aggressive acceleration significantly drain the battery. Therefore, while a 1,000-mile range is technically achievable in a laboratory or a controlled test track, a daily driver might realistically see closer to 700 or 800 miles. Even so, this remains a massive jump compared to current standards. But increasing range is not just about battery capacity. It is about weight and efficiency. To reach these numbers, the battery must remain lightweight while storing more energy. This leads us to the most talked about claim: 10-minute charging. This specific promise grabs the most attention because charging time remains the single biggest deterrent for potential EV buyers. Even with today's most advanced DC fast chargers, it typically takes 20 to 30 minutes to reach an 80% charge. So, how can CATL achieve a full charge in just 10 minutes? The theoretical answer lies in solid-state chemistry's ability to handle high power without overheating. But in practice, the primary enemy of fast charging is heat. Pumping massive amounts of electricity into a battery generates intense thermal energy. If this heat is not perfectly managed, it can degrade the battery's internal structure or even pose safety risks. Furthermore, there is the massive infrastructure challenge. For 10-minute charging to be viable, we need ultra-high-power chargers that simply do not exist at scale today. Supplying that level of electricity to charging stations without crashing the local power grid is a logistical nightmare that cities are not yet prepared for. Beyond charging, there is the hidden side of new technology that often goes unmentioned: manufacturing. Creating a perfect solid-state battery in a sterile lab is one thing. Producing millions of units with zero defects is another. The manufacturing process for solid-state cells is incredibly precise and complex. In traditional liquid batteries, filling the electrolyte is relatively straightforward. In solid-state production, every layer must be perfectly aligned and bonded. Even a microscopic crack or a tiny air pocket between the solid electrolyte and the electrode can cause the battery to fail prematurely. This is the main reason why many automotive giants have struggled to move from prototype to production line. Then, there is the inescapable factor of cost. Every new technology begins as an expensive luxury. Advanced materials, high-precision machinery, and low initial production volumes make solid-state batteries significantly more expensive than current lithium-ion versions. If the battery makes the car too expensive, mass adoption will stall. In the hyper-competitive EV market, price is the ultimate decider. Another concern is durability. During the natural cycles of charging and discharging, battery materials physically expand and contract. In a solid-state system, this mechanical stress can lead to the formation of dendrites, tiny, needle-like metallic structures that grow inside the battery. If these dendrites puncture the solid electrolyte, they can cause a short circuit. Controlling this phenomenon over the 10 to 15-year lifespan of a vehicle is one of the greatest engineering puzzles of our time. Finally, there is the issue of temperature. While solid-state batteries are safer in extreme heat, some solid materials actually perform poorly in extreme cold. For drivers in northern climates, this could mean a significant drop in efficiency during winter months. Integrating these batteries into a vehicle's cooling and thermal management systems requires a total redesign of the car's architecture. This is not a simple plug-and-play upgrade. It is a total transformation of the battery ecosystem. CATL's claims are grounded in real progress, but the road to 1,000 miles is paved with technical challenges that must be solved before you can buy one at your local dealership. The most compelling question remains: if this solid-state technology truly arrives, what happens to the industry titans like Tesla and BYD? The EV sector is already a high-stakes race, and whoever captures the battery breakthrough captures the crown. First, let's consider Tesla. Tesla is widely regarded as the global leader in software, integration, and charging infrastructure. Their supercharger network is the gold standard, and their vehicles are optimized for extreme efficiency. However, Tesla's core strategy has always been the refinement of existing lithium-ion technology, lowering costs through massive scale and improving energy density incrementally. If CATL successfully scales solid-state batteries and offers them to Tesla's rivals, the competitive landscape could shift overnight. Tesla's primary advantage, its superior range and charging ecosystem, could evaporate if competitors begin offering 1,000 miles of range and 10-minute charging cycles. But Tesla is not a company that remains stagnant. They are investing heavily in their own battery research, such as the 4680 cell and advanced dry electrode processes. It is highly likely that Tesla will either adapt by integrating solid-state tech or by pushing an alternative that offers similar performance at a lower price point. Then we have BYD. Unlike almost any other car manufacturer, BYD is vertically integrated to its core. They manufacture everything from the microchips to the batteries to the final vehicle. Their current Blade battery is already a benchmark for safety and cost efficiency. If CATL brings solid-state batteries to the commercial level, BYD faces two paths. Either partner with their fellow Chinese giant or accelerate their own internal solid-state development. Given BYD's history of rapid adaptation and cost control, they may be the first to bring this high-end technology to the mass market at an affordable price. But the competition doesn't stop in China or California. Global players like Toyota, Volkswagen, and Hyundai have been pouring billions into solid-state research for decades. Toyota, in particular, has long claimed to be on the verge of a solid-state breakthrough. The battlefield has shifted from who builds the best car to who builds the best battery. The winner will be the one who balances three pillars: range, charging speed, and affordability. Another fascinating angle is the rising power of the battery suppliers themselves. Companies like CATL, LG Energy Solution, and Panasonic are becoming more influential than the car brands they serve. If CATL is the first to scale this technology, they cease being just a supplier. They become the kingmaker of the industry. They will decide which manufacturer gets the best tech, at what price, and in what quantity. Power is shifting from the traditional automotive headquarters to the gigafactories of battery producers. Now, the most practical question for you: when can you actually buy this? While 2026 or 2027 are often mentioned, the reality is that lab-to-market transitions take time. We will likely see early, low-volume versions in premium luxury cars or specialized fleets by 2027. However, the true mass-market explosion, where a standard family SUV offers these specs, is more realistically expected between 2028 and 2030. This transition will be gradual, starting with high-price segments before trickling down to the average consumer. Once it arrives, the impact on daily life will be profound. The range anxiety that has plagued the EV movement for a decade will vanish. Road trips that once required meticulous planning will become as spontaneous as they are in petrol cars. Charging will become a 10-minute break for a coffee rather than a 45-minute logistical hurdle. The total cost of ownership will plummet as batteries become more durable and efficient, requiring less maintenance and offering longer lifespans. This is not just an upgrade. It is the final nail in the coffin for the internal combustion engine. As we stand on the precipice of this change, it is clear that the future of mobility is being built right now in the laboratories of companies like CATL. If you want to stay ahead of these massive shifts in technology and industry, make sure to subscribe and stay tuned for our upcoming deep dives. The road ahead is long, but with 1,000 miles of range, we are finally ready to travel it.